Greetings everybody. So our group consisting of Manas Abhyankar, Yash Breed and Pranav Nair are going to present you a topic, summary on image upsampling and downsampling filters. So we'll be going through the following: introduction, downsampling, upsampling, interpolation, filters, experiments, and a conclusion. So starting with what is sampling. So basically a digital image is a 2D array of size basically m cross n, where m is the number of rows and n is the number of columns. A digital image is made up of a finite number of discrete picture elements called a pixel. Grid is usually a rectangular point grid with equal spacing, and grid size defines the spacing of pixels, often same spacing in all directions. So why is sampling required? The output of most image sensors is an analog signal, and we cannot apply digital processing on it because we cannot store it. And we cannot store it because it requires infinite memory to store a signal that can have infinite values. So we have to convert an analog signal into a digital signal. So to create an image which is digital, we need to convert continuous data into a digital form. There are two steps for doing it: sampling and quantization. Next slide. Downsampling. So basically downsampling is a reduction in spatial resolution while keeping the same 2D representation. So it makes the data of a more manageable size. Also, pixels from high resolution image will their intensity to the pixels of low resolution image. This reduces the dimensionality of the data, thus enabling in faster processing of the data. It is sometimes confused with image compression, which is a different thing and serves a different use altogether. Here, we are concerned with just the shrinking of the image. There are many algorithms used and for downsampling, namely MIPMAP, box sampling, and sync. Next, we'll be going through upsampling. So it is nothing but the inverse of that of downsampling. That is to increase the number of rows or columns, or basically the dimensions of the image. So when downsampling, our intention was simple and clear, but with upsampling, it is not that simple. We need to somehow increase the dimensions of the image and fill in the gaps. A sensible approach to adding these new columns will be to interpolate the new data between these rows and columns. It improves anti-aliasing filter performance and reduces noise. There are many algorithms used in various techniques for downsampling, namely nearest neighbor interpolation, bilinear interpolation, bicubic, spline interpolation, and generalized bicubic interpolation. Next slide, interpolation. So what is interpolation? So basically an image interpolation occurs when you resize or distort your image from one pixel grid to another. Image resizing is necessary when you need to increase or decrease the total number of pixels. Research on interpolation techniques is of high value, especially in medical imaging domain, where the required quality and resolution of obtained images, such as magnetic resonance imaging, that is MRIs, must be as high as possible. Reconstructions of non-uniformly sampled volumes, such as that of viruses, are also accomplished with the aid of interpolation. Some techniques such as CAD, that is computer-assisted diagnostics, and CAS, computer-assisted surgery, rely on certain resolution constraints, either for identifying patterns in diagnostics or for providing high-fidelity imaging for specialists. A study of image interpolation in medical imaging research is of extreme importance for reconstructing accurate samples of computed tomographies, MRIs, DSS, that is digital subtraction angiography, and PETs, that is positron emission tomography. Even though most of the research performed in regards to interpolation is tied to the medical imaging field, research has also been performed on various other types of images. The metrics used in either of them are dependent on several aspects regarding their application.
Next, we'll be going about filters. So, what are filters and why do we really need filters? So, as we understood that downsampling simply means the removal of a specific number of samples at certain fixed intervals, and upsampling is the addition of a fixed number of zero-valued samples at fixed intervals. So, why are filters even required? To understand this, we must first understand what filters are. Filters are certain mathematical functions which are used in the elimination of frequency components from a signal. There are low-pass filters which keep frequencies from 0 to a specified value, high-pass filters which keep frequencies from a certain value till infinity, and band-pass filters which keep frequencies from between certain specified values. The most common application of these filters is noise removal, where certain frequency components which are most likely noise are eliminated, and these noise components are generally at the infinite end of the spectrum. This is an example of an image. As you can see, there are white spots in the image, and all of them were removed in the filtered image. So uh, if you capture an image from your phone camera, for example, and view it, it will look like the image which you have already captured. It is an identity transformation. But now if you zoom into the image becomes blurred because your phone applies direct upsampling by duplicating the values already present in the image. In short, it just takes the nearest neighbor and duplicates its value in its own self. So the pixels in the image appear a lot more prominent than they originally are in the original image. Similarly, if the image resolution is lower, then too the image appears blurred due to the same reason, since downsampling was performed by a phone as is without any sort of processing. So to explain it technically, let us take the example of a sine wave. So if we perform the FFT of a sine wave, then on the positive side of the spectrum, it has only one frequency component corresponding to the frequency of the sine wave and its amplitude at that coordinates. But suppose if we perform sampling on it at a particular sampling rate, then it is not a continuous wave, it is a discrete wave. So we get these intervals in between the sine wave. Now, since we are humans, we can understand that it is a sine wave, but the computer cannot. So, when there is any sort of discontinuity in any sort of wave, this includes sine waves as well, then by the concept of Fourier transform, we can say that it is a superposition of pure continuous sinusoidal waves. But since when we downsample the continuous sine wave by actually sampling it at a sampling frequency, we get a lot of sine waves in the frequency domain, and thus the known amplitude ratio which was present in the frequency domain, it turns into, you can say, a sort of spread out into the frequency domain, which is also known as spectral leakage. So we cannot downsample a wave to an arbitrary ratio, since it can cause aliasing in the signal by virtue of Nyquist theorem. We want the signal to retain its character even if it's no more continuous. We now move to the frequency domain so that a discrete signal and apply a filter which removes the unneeded frequency components of the signal. Thus, the frequency components which are higher than half that of the downsampled rate are removed, and thus the Nyquist theorem is taken care of. This is important so that aliasing is not present inside the filtered signal. In upsampling, generally what we do is we add zero values in between the original values to artificially bump up the sampling rate. When we do this, yet again the signal loses its original nature, and we do not want that. We want it to resemble the original signal, albeit in a much sharper form. Thus, we again go to the frequency domain and filter out the frequencies there. The final result which you obtain is a much more smoothened form of the signal, which now resembles the original. So we shall be talking about different types of filters here. So the first are polynomial filters. They are also known as polynomial interpolators. These are some filters which can be applied in the spatial domain as well as in some cases the frequency domain also. Now let us take the example of a box filter. The formula for the box filter is the value returned by the box filter is 1 when the energy or the absolute value of that of the input is less than or equal to 1 and a 0 otherwise. So if the value is less than or equal to 1, it will return a 1, and if it is greater than or equal to 1 in its absolute value, it will return 0. Now we shall be moving forward to sinc functions. So without before understanding sinc functions, okay, before understanding window functions, we must understand what sinc functions are. The formula for the sinc function is as follows. It is f of x equals sine pi of x divided by pi of x. So the sinc function is considered as an ideal low-pass filter in the frequency domain, since it features a drastic cut off at pi by 2 and 0 thereafter. So basically what it does is, in the frequency domain, any frequency greater than pi by 2 are cut off, and any frequencies less than pi by 2 are retained inside the signal. If we look at the filter in the time domain, we can see certain ripples in the function graph which extend to infinity. Here's where the problem becomes obvious. When we say we want a filter which will only act in a given interval of time where the signal is actually present. In other words, what we need is a finite impulse response filter. To solve this problem, we take window functions. So what are window functions? Window functions are functions which apply a certain sort of window to the sinc function in order to alter its shape. The main intention is to try to balance its ideal low pass properties in the frequency domain with its infiniteness in the time domain. So basically what we want to do here is the sine filter is an ideal low pass filter. So we want to retain that property of it being an ideal filter to the greatest extent, as well as we want to cure its infiniteness in the time domain so that it becomes a finite signal in the time domain or close to a finite signal in the time domain. So one of the simplest window functions is the box function, which essentially leaves the sinc function as it is. The second most simplest are B splines. So what are B splines? For example, if you draw a sort of a pattern of dots and try to join it, what you get is a curve which passes through the dots. But if you try to do it mathematically with the help of a computer to find the, we can say the shortest possible curve in between those points, what we get is a B-spline. So as you can see here, B-splines are curves which are used for approximation of an equation going through a given number of points.
So I'll be explaining some experiments conducted on the above observations or the things that we have learned till now. So the coming down to the first experiment, the downsampling filter in this experiment is the Hamming window synced with window size 3, and it performed as all the Windows sync approaches mentioned with an increased width from 7, 9, and 11. B-splines of the same orders and the Appleton Gaussian kernel of 5 are also taken into account for the same window length. Some kernels stop performing as per expectations once the window is increased beyond a certain point. This is mainly due to the fact that the ripples induced by the sync-shaped interpolation kernel create the so-called ringing artifacts that bring the image quality down. The analysis reveals that the Welch and the sine window with a window length of 11 also expose a good MSSIM, which is the mean structural similarity value, as well as a PSNR, which is the peak signal to noise ratio. Also, Langzhou's windows are exposing good quality and monotonic characteristics with regards to the window length. The second experiment conducted is as follows. The second experiment relies on the validation of previous observation that the Hamilton window is indeed the best decimator in the current process. The author considers a fixed upsampling kernel, namely the windowed sync function, with a Langzhou's function of width 4. Author varied the shape and width of the decimator instead of those of the interpolator as in the previous experiment. The author looked up only for functions in the windowed sync family and noticed good overall behaviors for the Hamming window. Even though an anomaly tends to appear from the window of size 3 in that its performances are weaker than they are in size 5. That seems to be the case for multiple decimators, especially for the Langzhou's filter, which appears to have a drastic turn for the worse as the window is increased for PSNR, which is the peak signal to noise ratio, and MSSIM, which is the mean structure similarity. The conclusion that can be drawn from this experiment is that the best decimator achieved using the approach is Hamming window sync function of width 3. Coming down to experiment 3, from the experiments 1 and 2, the best decimator slash interpolator pair is taken and applied them on more examples. The aim was to discover the intrinsic image properties that determine a certain behavior. As performed in the previous experiments, the author also used a scale of 4 to compare the results and ran the test on multiple images from the dataset. Using a Hamming window sync of size 3 as the decimator and a sine windowed sync of 11 as an interpolator. From the previously done analysis in the frequency domain, the image yielding good results has a very low frequency spectrum. As most of its energy is concentrated in the center of the spectrum, little to no information is lost when low pass filtering it as a result of the interpolation process. The image that produces bad interpolation results has a wider bandwidth and is thus more susceptible to losses of information due to the low pass filter applied. And with that, we come to the end of our presentation. Thank you.